Welcome students to this video on Sturm Liouville problems. This is one of the most important aspect of the study of ODEs. Okay, so what is this topic about? See, we are essentially interested in the equation like this, a second order equation given by P naught of x y double prime, okay, plus P1 of x y prime plus P2 of x y equals to R of x. Okay, let's call that 1. So this is your second order equation. Is it okay? Now this is defined on some alpha beta, defined let's say in alpha beta, and here we are assuming P naught, P1, P2 and R are to be smooth. Okay, so maybe sufficiently C1 or C2, okay, whatever is okay that you can choose, is not a big problem. And we also have the boundary data, right? What is the boundary data? So first of all, we'll call it a L1 of y. Let's just call it like this, which is given by A naught of y at the point alpha plus A1 y prime at the point alpha plus B naught y at the point beta plus B1 y prime at the point beta. Let's just call that to be A, and there is another condition L2 of y, which is again the similar sort of condition but with C naught and D naught. C naught y at the point alpha plus C1 y prime at the point alpha plus D naught y at the point beta plus D1 y prime at the point beta. This is B. This is okay. So L1 and L2, if those two are these two sort of conditions are there, so basically 1 along with these two conditions here, AI, BI, CI, DI, A and B are constants. Okay, are constants. Now we wanted to study this problem. Now you see this problem, if you remember, we have seen that for some values it will depend on the value of the initial data, depend on L1 and L2, but the thing is this problem may have solution, may have unique solution, may have no solution, or may have infinitely many solutions, right? We have already seen that part. Now the thing is this, you see, a very important aspect in mathematical physics, okay, is to determine, see, if let's say if we put lambda over here, let's say a lambda over here, okay, let us, so essentially let me write it this way. Let's say now if we have a boundary value problem, which will look like this, P y prime whole prime, okay, plus qy plus lambda ry, okay, equals to 0. Let's just say if we have a problem like this, is it okay? Right. So see, R is here I wrote R like this, so basically think of it as R to be 0, and the thing is P2 looks like this, okay, Q plus lambda R, sorry, yes. And this sort of equation, basically in mathematical physics what happens is there are many different situations where you have to determine the value of this parameter lambda, okay. So the question generally arises as determine lambda, okay. So the value of lambda, that is here you see a lambda is in a complex number C, that's what we generally is assumed, okay, for which non-trivial solutions exist, okay. See, it is not that this is only from mathematical physics, even doing solving some PDs and all, we actually are going to need this sort of problem. So this is a very, very important class of problems. These are called Sturm Liouville boundary value problems, okay. So we are going to study this problem. So basically what is the equation? The equation is given by this, let's just call this 2, yes, and so 2 along with maybe I can write it like this, right? Maybe I can write this as okay, let me I should introduce the problem properly, okay. So essentially, okay, so let me do it properly, okay. So you got the idea. Essentially, this is the equation, and for this equation you have to find. So you have to find lambdas for which non-trivial solutions exist. You do realize that for all lambda, it may happen that for some lambdas there are one solution, unique solution, right? For some lambda there is no solution. For some lambda there will be infinitely many solutions. Okay, so you have to keep track of such lambdas for which there are non-trivial solutions. Okay, and what is the boundary data that we have to determine. Okay, so what I am going to do is maybe introduce the problem in the next page properly. Let me do it this way. See, the thing is, first of all, in one, let me introduce it in this way. See, consider 1 with Rx equals to 0. So basically the homogeneous problem, Rx equals to 0. Clear? Now you see, for the homogeneous problem, what happens is this: if you are, this problem is in the general form, right? Now if you multiply it properly with the integrating factor and all, we know we can actually write it in terms of a self-adjoint operator. Okay, so write one in terms of self-adjoint operator, adjoint operator. Okay, and then what happens is, if we can write it in terms of self-adjoint operator, then it will look like this: py prime plus qy. Right, this whole form. See, then this p naught y double prime plus p1 y prime plus p2 y may be written as, okay, we have seen, right? We can write it as p y prime whole prime plus qy. Okay, now the question is this, that let's say that if this is equals to let's say lambda times some ry. Okay, lambda can be positive, negative, doesn't matter, but lambda some it can be complex also. So let's say we want to find out for which values of this is equals to lambda times ry. Okay, then these sort of problems are called Sturm-Liouville boundary value problems. If you write it properly, you see what is happening is this. Let's say this is the operator L of y, and let's say r is 1 for now. Then it will look like lambda times y. You see, this sort of equation are the eigenvalue problems, right? So basically we are trying to find out the eigenvalues of L and the eigenfunctions, of course. Okay, so these sort of equations are called eigenvalue problems. So basically Sturm-Liouville problems are called eigenvalue problems because of this reason. Okay, now so let me now formally introduce the problem, and then we are going to look at some properties of this. Okay, so consider the differential equation. What is the differential equation? It is given by p y prime whole prime. Okay, see, first of all, again, anyways, these Sturm-Liouville boundary value problems we are always going to consider a self-adjoint differential equation. Okay, so plus q y plus lambda r y, okay, equals to 0. That is the equation given to us. Yes, and of course p and q. Okay, let me write it down. So p and q are continuously differentiable. Okay, p and q are continuously differentiable. This is given to us. Okay, what is lambda? Lambda is a parameter. Okay, for the starters, what we are going to do is we are going to assume lambda is some number, is a parameter which is varying at in c. So basically lambda will be from c. That's what we are going to assume initially. Okay, okay, so this is there, and very important property. Yeah, so these properties are very important in order for this problem to work. Okay, p and r are positive. Please remember this thing, very important. Okay, without these properties, none of the things which I am going to do is going to work. Okay, so first of all, p is this, yeah, the first coefficient. R is this, the coefficient corresponding to lambda. Those two problems. So okay, we are going to assume the problem. You see, first of all, we are going to write it like this: Ly plus lambda ry equals to 0. Clear? This lambda corresponding to this r corresponding to lambda will be called a weight function. This is called a weight function. Is this okay? We will call it like this, and we will write this operator like this: Ly plus lambda ry equals to 0. Is it okay? Yeah, this is the form which you are going to write it. Again, if we are writing like this, please remember p has to be positive. The first coefficient p corresponding to py prime whole prime. Okay, this p has to be positive, and along with that lambda, the r which is along with lambda, the weight function r, that has to be positive. These two condition is vital for this sort of thing to work. Is it okay? Otherwise, you know, the problem is this. Without this, if you want to do this problem, so what happens is, first of all, you know that if p is 0 or something like that, then I mean, we can have that this is not a regular problem, boundary value problem. Okay, so this will be in this case a singular boundary value problem, and of course we are also assuming all of these in a closed interval alpha beta, that is also there. Okay, closed interval alpha beta. Why? Because in that, again, we are basically looking at regular boundary value problem. Okay, right. You see, of course, what are the boundary data? Along with the boundary data, what is the boundary data? We are going to assume this boundary data: a naught y at the point alpha plus a1 y prime at the point alpha is 0. Okay, and d naught y at the point beta plus d1 y prime at the point beta is 0. This is okay. These are the two boundary conditions which you are going to assume along with this equation. So let us, for now, let's call this equation as star. Okay, the whole thing, yes, the equation along with the boundary. So maybe I can write it here, star. This is the star problem. Okay, this is the problem which we want to study for next few 1 or 2 I mean, you know, videos. Whenever we are talking about Sturm-Liouville boundary value problem, we are going to look at this particular problem. We will call it a Sturm-Liouville boundary value problem. Is it okay? Sturm-Liouville boundary value problem. Okay, and generally speaking, we also like to call it as a eigenvalue problem also. That also is generally done. Okay, and please remember, this is the data which we have considered: p, q, the interval I is alpha beta. So this is of course a regular boundary value problem. So it is generally there. It is also called a regular Sturm-Liouville boundary value problem. Is it okay? Because this is a regular data, right? Regular boundary data. This we already know. So it is. It looks like this. Okay. See, the thing is, the lambdas which you are going to find. So basically, a small note here. Now, what is the problem? The problem is to find lambda, right? Those will be called as eigenvalues, right? Eigenvalues, clear? And the corresponding okay, non-trivial solutions. Is it okay? This is the problem, corresponding non-trivial solutions you have to find. Okay, and we will call it a phi lambda of x, right? So any solutions of this for a given lambda, any solution will look like phi x lambda, right? Which is again a function, so it's sufficient regularity. Yes, so in C2 of I is I, so this is defined in I, right? All of this is in I, which is alpha beta, let's say, if you remember, and this is finite, close bounded set, I to R, that sort of function. Okay, non-trivial function. This will be called eigenvectors. If you remember, this is called eigenvectors, right? Or eigenfunctions also we will call it. It's not a problem. Synonymously, it is also called eigenfunctions. So I am going to call it eigenvectors or eigenfunctions, whatever. Everything is fine. It's not a problem. Okay. Now, if you put all a set of all eigenvalues, okay. Now again, also the set of all eigenvalues. So if you take the set of all eigenvalues together, right, of a regular problem of star, that set is called the spectrum. Is called the spectrum. Okay, what is spectrum of what? Spectrum of some operator, right? So the operator is given by L, which is P y prime whole prime plus Q y. That's the operator. Okay, so I mean that is as you understood. Is it okay? Right? So that is the whole problem. That's the introduction of the problem. Okay. So now let's work out one example, and then we will go to the theory part. So first of all, how do you compute such an eigenvalue and eigenfunction? Let's just look at that. So you see, first of all, consider this problem. Consider y double prime plus lambda y equals to 0. Is it okay? And then y0 equals to y at the point pi equals to 0. Yes, if you remember, see here, if you assume p is of course 1, here p of x is identically equals to 1. Okay, what is q of x? Q of x is essentially 0, and what is r of x? R of x is essentially 1. Okay, so you see here for the problem p and r has to be positive. Q can be anything, I don't care. Q can be negative, positive, whatever, as long as q is continuous, it's fine. Okay, and the data is given on 0 and pi. 0 and pi, what sort of how do I put it? What sort of interval it is? It is a closed and bounded interval, right? So what sort of problem is it? Can you think of it? What is it called, this sort of problem? So this sort of problem is called regular Sturm-Liouville boundary value problem. Okay, so we call this sort of problem is, what is it? Regular. So I will write it like this, regular Sturm-Liouville boundary value problem. Is this okay? We'll call it this, right? Okay, now how do you solve this thing? So first of all, see, what we are going to do is, I'm just going to concentrate on lambda in R. Okay, so we are going to concentrate on lambda in R. So what I mean by this, see, generally speaking, lambda can be in C, right? But the thing is, we are not really interested in C right now. Why not? That will be covered in the theory part. Okay, so you do not have to look for lambda in C. So essentially, if there are lambdas, okay, for which non-trivial solutions exist, those lambdas has to be real for this sort of problem. Okay, that comes from theory, so you don't have to worry about it. All you have to worry about it is the real lambdas. Okay, so first of all, so what can be the cases? First case is either lambda is 0, or lambda can be non-zero, or a positive or negative, right? Okay, so first of all, if lambda is 0, okay, then what happens to this equation? Y double prime equals to 0, and the general solution y of x will look like c1 plus c2 of x. Is it okay? And c1 c2 is in R. C1 c2 is in R. Okay, and you see it satisfies these two equations, and you see 0 equals to y at the point 0. That is nothing but c1 plus c2 times 0. Okay, that will give you c1 is 0. Now if c1 is 0, if you are putting it like this, then y is c2 of x, right? Now therefore what we have is y of x is nothing but c2 of x. Now it also has to satisfy the other condition. So what is the other condition? 0 equals to y at the point pi, right? So which is nothing but c2 times pi. So c2 times pi is 0. That will imply c2 has to be 0. Okay, hence c1 and c2 is 0. So yx identically equals to 0. Is it okay? That is the only solution available. Now you see, what is the question? The question is this: you have to find, please remember, you have to find lambdas for which non-trivial solution exists. See, this is the homogeneous problem, right? So for any lambda, trivial solution exists, right? See, let me put it as a small remark. See, these regular Sturm-Liouville boundary value problems, they are homogeneous problems. So for any lambda, trivial solution is always a solution, right? For any lambda, trivial solution exists. Is it okay? Now the thing is, this trivial solution is fine, but what about the other non-trivial solutions? Okay, now you have to find, if you have to find something like that, then you have to work out. So basically you have to find out lambdas for which non-trivial solution exists. So here you see, if lambda is 0, you will see that lambda yx equals to 0 is the only solution. Is it okay? So the thing is, since this is the case, therefore lambda equals to 0 is not an eigenvalue. Is not an eigenvalue. Is it okay? It's not an eigenvalue. Okay, right. So this is case 1, let's say. Case 2. Let's say lambda is non-zero. So if lambda is non-zero and lambda can be positive, negative. So lambda is, let's say, mu square. Okay, mu not 0. Clear? So it's non-zero basically. So in that case, then the equation which you have is y double prime plus mu square y equals to 0. Is it okay? And that will imply yx equals to c1 times cosine mu x plus one second. This is plus minus m square. What is the solution? M square plus mu square. Yeah. So c1 plus c2 times sine mu x. Sine mu x. Yes, right. That's what the solution is. Yes, I hope this is, I am correct. Yes, fine. Okay. Now c1 and c2 is of course in R. C1 and c2 is in R. It is given. Okay. Now see, if this is the case, now you have to satisfy that equation. So what is it? First of all, the first equation is this: 0 equals to y at the point 0. And what is it? Y at the point 0, c1 times sine mu 0 plus c2 times, I have wrote it as sine cosine, right, or cosine sine. So I should write it properly. So cosine mu x plus sine mu x. So I should write it like cosine mu 0 plus c2 times sine mu 0. Is it okay? Yes. Now you see, sine 0 is 0 essentially. Okay. So c1 times cosine 0 is 1. So that will imply c1 is going to be 0. Is it okay? So therefore, now the second condition is y equals to 0 equals to y at the point pi. Okay, which is equals to c2 times sine mu pi. That's what you have, right? Yes. Now you see, is it okay? Because c1 is 0, right? So the only thing which is remaining is c2 times sine pi x. So basically now y equals to c2 times y pi x, and it satisfies y at the point pi is 0. So basically c2 times sine pi y mu pi is going to be 0. Is it okay? Now, of course, mu is non-zero. Yes. So sine mu pi is not going to be 0, right? Generally speaking, c2, let's say c2. So here what we have is c2 times this sine is 0. Okay. Now if c2 is 0, see, if c2 is 0, c1 is 0, c2 is 0, then we have, what we have is a trivial solution in that case. Okay. We do not want trivial solution because that's not an interesting case, right? Okay. We want non-trivial solution. So we have trivial solution. If c2 is 0, we have trivial solution, which we don't want. Trivial solution. Okay. So if c2 is not 0, what happens? If c2 is not 0, then you have non-trivial solutions. Okay. Then y of x, since sine of mu pi is 0. Okay. If c2 is non-zero, then sine of mu pi has to be 0. So now what does that mean? Sine of mu pi has to be equals to sine of n pi. That's the only case when they are going to be 0. N is in z. Is it okay? Otherwise there is no other option, right? Okay. So if this is the case, what does that mean? What is pi? Pi is nothing but n. N is in z. Is it okay? Yeah. So what it means is to see, if we are looking for non-trivial solutions, okay, positive eigenvalues, lambda positive. You see, this is lambda equals to mu square. So positive. For positive eigenvalues exist if mu equals to, so basically what is the corresponding eigenfunctions? Mu equals to n. Okay. So what is mu? Mu is lambda, root lambda. So lambda is mu square, right? So therefore, what are the eigenvalues? Eigenvalues are positive. Eigenvalues, okay, are given by see, lambda, eigenvalues are lambda, which is mu square, and mu square is n square. So eigenvalues are given by n square. Okay, n is in n, let's say. Z also doesn't matter, right? It is n square basically. Huh? And what are the corresponding eigenfunctions and eigenfunctions? What are the eigenfunctions? What are the solutions of this? See, if lambda is n, the solution is given by, see here, after all of this, what is y of x? Y of x is nothing but c2 times sine mu x, right? That was the solution. Huh? And then that solution satisfied this y at the point pi equals to 0. Okay. So now you see, if mu equals to n, then yx. So basically for those, what is your function which satisfies? Sine of nx, right? Yes, constant times sine of nx, but constant can be 1 also. Any constant multiple is fine. So basically it is sine nx, okay, and eigenfunctions are given by r sine nx, okay, and n is in for now let's just say n. It's not a problem. It can, n can be z also, but it doesn't matter. Huh? So it's basically the same thing. Okay, so you see, these are the things, right? So essentially what we can say is the eigenpair. What is an eigenpair? Eigenpair is the eigenfunction with its corresponding vector or function. Okay, so eigenvalue with its eigenvector. So eigenpair is r. Let's just write it as r n square sine of nx. Okay, n is in n, let's say, or z. You can put it as z. Huh? I think it will be much appropriate. Okay, these are the eigenpairs. Is it okay? So let us take here to be z. N is in z. Is it okay? So these are the eigenpairs. Eigenpair is eigenvector, the eigenvalue. The first thing is eigenvalue, and the second part is the corresponding eigenfunction. Okay, right. Now, so we have these positive eigenvalues. Okay, what about negative ones? So now, case 3. If lambda is how do I put it? Let's say negative, huh? So minus mu square, mu non-zero. Let's just take it like this. Is it okay? Then what happens? Let's just check that. What happens? See, now y, the equation turns out to be y prime minus mu square times y equals to 0. Okay, we can solve this equation, right? And if you solve it, the solution which you are going to get, yx equals to c1 times cosine mu x plus c2 times sine mu x. Sine mu x, right? Yes. Sorry. This shouldn't be the case. I am writing this mistake. E power mu x plus c2 times e power minus mu x. Okay. c1, c2 is in R. Here. Now, it has to satisfy those two equations again. Again, 0 equals to y at the point 0, which is equals to c1 times e to the power mu times 0 plus c2 times e to the power minus mu times 0. Okay, so that will give us c1 plus c2 equals to 0. Is it okay? So that is your first equation. Let's just put it. Okay, and another one, 0 equals to y pi mu equals to 0. That is there, right? So the second one is 0 equals to y at the point pi, which is c1 times e to the power mu pi plus c2 times e to the power minus mu pi. Okay, so this is 2. Now it is quite clear that from 1 and 2, okay, what do you have? c1 equals to c2 equals to 0. There is no other way. Okay, so please check this part, because the determinant is basically non-zero. So trivial solution is only going to be the solution, or it's the only solution. So basically, please check this part. Okay, so c1 equals to c2 equals to 0. Therefore, yx is identically equals to 0. It's the only solution. is the only solution. Only solution. Yeah, what does that say? That says that there are no negative eigenvalues. Is it okay? So that will imply there does not exist any negative eigenvalue. Is it okay? Yeah. So what did we have? We have positive eigenvalues. Okay, along with eigen functions, which is given by sine of nx here. Yes, that's what we have. Okay, and the thing is, we do not have any zero eigenvalue, or we do not have any negative eigenvalue. That's what. So this is how you solve these problems. Now, a very important part here is this. See, we have assumed, where is it? We have assumed lambda is in R. We did not look at the complex thing. What happens if lambda is complex? Yes, and those things will be taken care of now. Okay, so what we are going to do is this: we are going to define some new theory. Okay, and with the help of that theory only, I will justify why we don't have to consider the complex things. Okay, right. So first of all, let's write down a definition. What is the definition? The definition is the set of functions okay, the set of functions phi n of x maybe I can write it this way: n equals to 0, 1, 2, okay, each of which are piecewise continuous. For now, we are just starting with piecewise continuous. Continuous. See, this definition which I am writing has nothing to do with the theory. Is it okay? So that is why I am just giving it for the most general case. Okay, but the thing is, we are not going to need so much general cases in our this theory. Okay, so this is just for definition in terms of definition. So the most general way of putting it, which are piecewise continuous in an infinite or finite set. Okay, infinite or finite interval alpha beta. Okay, now is said to be orthogonal if with respect to Rx, with respect to a non-negative function Rx if phi n the inner product of those two. Okay, we will call it an inner product of phi m and phi n. Given two functions, the inner product is defined like this: alpha to beta phi m of x, phi n of x, r of x dx. This has to be 0. Is it okay? For all m not equals to n. Is it okay? And alpha to beta r of x phi n square of x dx is non-zero for all n. Yes. See, the thing is, if those two conditions hold, okay, this r of course is called, as I told you, this is called the weight function. Okay, so if these two conditions hold, then we call, the set, the phi n set, is a orthogonal set. Is it okay? Orthogonal set. Of course, if this non-zero, it is the integral Rx phi n square is non-zero, right? If it is the 1, then we call it a orthonormal set. Okay. So remark. If alpha to beta here, phi n square x dx, if that is equals to 1 for all n, then we call it then the set phi n of x n in n is called orthonormals. It's called orthonormal. Is this okay? Right, that's just a definition. Now you see one small detail which we need to understand here is this. See, for something like this to happen, the integral from alpha beta Rx times phi n square, let's say it is summable, right? Yes. For something like this to happen, we will assume that Rx only has a finite number of zeros. So this is assumed. Assuming, let me put it this way, assuming, see if you remember, or maybe we have assumed R is non-negative function, right? But we did not assume. Maybe I can. So okay, assuming R has finite number of zeros. Finite number of zeros. Is it okay? Now, what's the idea? See, basically what is happening is this. Let's say in Rn, I will give you some motivation. In Rn, what happens is this: two functions, 2 points, vectors x and y. They are orthogonal to each other. X dot y, basically they are perpendicular to each other if x dot y is 0. Yeah. So in Rn, what is the inner product? Inner product is given by x dot y. That's the inner product. So basically the dot product, right? Now let's say in a space like this, let's say C of alpha beta in this sort of set. Okay, you have two functions f and g. Yeah, and we say they are perpendicular to each other. But how are you going to define that perpendicular to each other part? Okay, that what we are doing is this. Basically, we are defining it as the inner product of f and g is given by integral fg, right, dx. Is it okay? And then if that is 0, then we call it orthogonal. So basically this is just a generalization. In a vector space, finite dimensional vector space Rn, if you have to define the inner product, you define it like a dot product x dot y, which is your usual thing. But in a vector space here, we can define it, you can think of it as the inner product space, and what is the inner product is given by integral fg dx. Okay, there can be others also, but this is the inner product which we are basically going to assume. Is it okay? Right. So orthogonal set, orthonormal set, clear, right? Now the thing is this. See, question is, does there exist an orthonormal set? I mean, orthogonal is it okay? So, but does there exist one? Can you show there is one? So you see, the thing is, let's look at this thing. The thing, sine of nx, n in n, n in n or n in z, it's not a big issue, but n in n for now. Let's just assume that. So this set, let's say, call it the set A. Yeah, you see, A is, we will prove that this is a orthogonal set. Is it okay? Right? And what is this orthogonal set? It is orthogonal somewhere, right? See, we say that two vectors, let's say 1, 0 and 0, 1, they are orthogonal to each other. Those two vectors is in some space, right? In some vector space, that is in R2. Yes. Here, they are orthogonal set, let's say, in C infinity also you can put if you want, but let's just put it at C1. C1 of, let's say, minus pi to pi, or 0 to pi also, it's not a problem, 0 to pi. Let's just say 0 to pi. So basically in this set, they are orthogonal. Okay, right. So how do you prove something like this? So in this case, what do you have to do? Alpha to beta. Okay. R in this case is 1. Yeah, so it is orthogonal with respect to the weight function r, which is identical equals to 1. See, r has to be non-negative. That's the only condition, and it has to have finite number of zeros. R is 1. If r is 1, all of those conditions are satisfied. So this is the orthogonal set with respect to the weight function 1. Okay, so how do you prove it? Sin nx times sin mx dx. Okay, now of course you can do this integration. So please check that this is going to be 0 if m not equals to n. Okay, so this you have to check it yourself. It is basically an integration, very easy stuff. Okay, and you can actually show that I mean the integral from and moreover and integral alpha to beta sin square nx dx sorry, I should write 0 to pi and not alpha to beta. I should write 0 to pi and again 0 to pi sin square nx dx. This is going to be most probably pi. Okay, so please check this part. Okay, you have to check it for all n in n. It is so what does it give you? It gives you that this is A is orthogonal set. Yeah? It's a orthogonal set with respect to the weight function r. So in C1 of 0 1 with respect to the weight function 1. Function wx identically equals to 1. Is it okay? That's just I mean one of the examples of orthogonal thing. Okay, now the important part is this. There are some theorems which you need to prove, and these are very important theorems. Okay, so the first theorem, these are the properties of regular Sturm-Liouville boundary value problem. Okay, the first theorem. So what is the first theorem? The eigenvalues of a regular Sturm-Liouville boundary value problem. I will writing like this. So please understand that this is just a shortcut. I don't want to write the whole thing down all the time. And what is the problem? Star. Yes, are simple. What does it mean? Let's just understand what does it mean. It means that if lambda is an eigenvalue, okay, and phi1 of x and phi2 of x, okay, are the corresponding eigenfunctions, So you do realize that eigenfunctions for one particular eigenvalue is never going to be unique, right? Because if phi is an eigenfunction, constant times phi is also going to be an eigenfunction. Is it okay? So phi1 and phi2, let's say there are two corresponding eigenfunctions for a given eigenvalue lambda. Yeah, what you can show is then phi1 and phi2 are linearly independent. So they cannot be linearly dependent. Okay, they are linearly dependent, so they cannot be linearly independent. Yeah, so they are linearly independent. So basically dependent. So basically what it means is phi1 has to be a constant times phi2. There cannot be two extremely different functions which are like linearly independent. Okay, right. So what is the proof? Now you see that phi1 and phi2 are both solutions, right? So phi1 and phi2 are both solutions of what are these solutions of? The solutions of star with lambda. Right? So this equation, if you write it with lambda, where is the equation? Sorry, where is the equation? I wrote somewhere, no? Star. If we write lambda, let's say lambda is an eigenvalue, then phi1 and phi2 both satisfies this equation. Is it okay? So, and with this boundary data, okay. So let me write it down. That will make life much easier. So therefore, p phi1 prime whole prime plus PQ phi1 plus lambda R phi1 equals to 0. Okay, and also this equation is there, P phi2 whole prime plus Q phi2 plus lambda R phi2, this is 0. Is it okay? We have also the boundary data, right? And moreover, and you have the boundary data A naught of phi1 at the point alpha plus A1 of phi1 prime at the point alpha is 0. Yes, corresponding to phi1, right? And the same thing also holds A naught, and I hope I wrote B. Let me just check that part. So the other one is A1 and A naught and A1, D naught and D1 I wrote. So let's write down D naught and D1, and this thing D naught phi2 phi1 at the point beta, phi1 at the point beta plus D1 phi1 prime at the point beta, this is 0. Yes, and similarly here phi2 also satisfies this equation. So A naught times phi2 at the point alpha plus A1 times phi2 prime at the point alpha, this is 0. Yeah, and correspondingly D naught phi2 at the point beta plus D1 phi2 prime at the point beta, this is going to be 0. Yes, so if phi1 and phi2 they are both the eigenfunctions corresponding to the eigenvalue lambda, then these all these conditions hold. Is it okay? Now you see, what does this condition say? It says that the Wronskian of phi1 and phi2 at the point alpha, this is 0. And similarly for beta also we can say the exact same thing. Okay, but there is, what it is saying is this: there exists a point alpha. Yeah, in that interval alpha beta there exists an alpha where the Wronskian of two functions are 0. Essentially that will imply the Abel's theorem, if you remember, that will imply phi1 and phi2 one second. Oh, sorry, what am I saying? One second. Sorry, I should do it in this way. Okay, so first of all, I will come to this. So essentially, first of all, let's just look at this. See, first of all, these two equations are there. Yes, what is this equation? If you write it down, it is L phi1 plus lambda R phi1 equals to 0. Yeah, this is equivalent to this. This part is equivalent to this. And this is L phi2 plus lambda R phi2 equals to 0, where L of y equals to P y prime whole prime plus Qy, right? That's your L of y. So those two are this is fine, right? Now you remember, if this is the case, you can use Lagrange identity. You remember I told you that we are going to use Lagrange identity later on. So we can use Lagrange here. So using Lagrange identity, one has that this equation, from these two equations, use the Lagrange identity, you are going to get Px times the Wronskian of phi1 and phi2, okay, at the point x is a constant c. C is a constant. You remember we did this. So please go back to this adjoint equation and exact equation part, that video. You are going to get this thing. Yeah, so this is by Lagrange identity, or Green's identity also you want to call it. It doesn't matter, but basically the same thing. You integrate one part, so basically we are going to get it. Yes, okay. Now you see this c, we have to find what this c is. Is it okay? Yeah, we have to find this c. See, the thing is, that is what I am trying to say. From here, from these two equations, what do we have? We have that this is nothing but the Wronskian of phi1 phi2 at the point alpha. This is equals to 0. Is it okay? This is what it is saying, right? Or even this is also saying the same thing. The Wronskian of phi1 phi2 at the point beta is 0. This is what it is saying. Okay. Now the thing is, if you remember, now P is non-zero, right? P is non-zero given to you. Okay, so we have to find the value of C here. What happens to the value of C? Okay, now since the Wronskian of phi1, phi2 at the point alpha is going to be 0, then what is C? So that will imply that C has to be equals to 0. There is no other way, right? Yes, I hope this is clear. See, Abel's theorem, phi1 and phi2 are both solutions of this equation, right? So if the Wronskian is 0 at one point, it has to be 0 everywhere, right? That's just the Abel theorem. So basically, if that is the case, then in this case, Wronskian of phi1, phi2 at any point x is going to be essentially 0. So in that case, C has to be equals to 0 because P is assumed to be positive. You remember, P is assumed to be positive. We have always assumed since P is greater than 0. So C has to be 0. Okay, now if C is 0, therefore what does it imply? It implies that phi1 and phi2 are linearly dependent. Linearly dependent. I hope this is clear to you. Okay, right. So what do we have for one eigenvalue? If you have two different eigenfunctions, this thing phi1 and phi2, then phi1 equals to C times phi2. That's what it is saying. So basically, the other way of saying it is that the eigenvalues are simple. So now let's look at the second important theorem, theorem 2. What does it say? It says that you look at the set of eigenvalues lambda n equals to 1, 2, so n is in n essentially. Okay, be the eigenvalues of a regular Sturm-Liouville boundary value problem. Is it okay? These are the eigenvalues of a regular Sturm-Liouville boundary value problem. Okay, and phi n. Is it okay? Phi n equals to 1, 2. This be the corresponding eigenfunctions. I am writing it in terms of set, but you do realize what I am trying to say. Corresponding eigenfunctions. Is it okay? Then the set phi n of x n equals to 1, 2, this set, okay, is orthogonal okay, in alpha beta with respect to the weight function Rx equals to 0. Weight function Rx equals to 0. Is it okay? So basically what it is saying is this, sorry, Rx equals to 1, Rx equals to 1. Okay, so what exactly is it saying is this, you see, if you have let's say lambda 1, lambda 2, it goes on, like lambda n, it goes on like this. Now corresponding to lambda 1 you have phi 1, corresponding to lambda 2 you have phi 2, corresponding to lambda n you have phi n. Now the relation, what is the question is this, what is the relation between phi 1, phi 2, phi n? The relation is this, they are saying they are going to be mutually orthogonal to each other. So phi m times phi n, if you indicate it with respect to Rx equals to 1, of course, it is going to be okay, maybe Rx is 1 not required. So with respect to the weight function, Rx is fine. Yes, don't have to work. Rx equals to 1 also will work, but the thing is generally here there is a Rx, so we don't want it. It's fine. So basically what I'm trying to say is this, they are orthogonal. So basically it means that integral phi m x phi n x times Rx dx, this is going to be 0. Is it okay? For m not equals to n, of course, for m not equals to n, this is going to be 0. This is what he is going to say. Now, before we prove this theorem, let me tell you why this is very important. See, essentially, this equation is important in the sense that it actually gives you a set. It actually, see, if you have a regular Sturm-Liouville boundary value problem, and if you can somehow find some set of eigenvalues and eigenfunctions for that, then that eigenfunction set will act as a set of orthogonal functions, right? Yes, So if you have to somehow, let's say for some problem purposes, you have to somehow produce an orthogonal set of function. Yes, what do? You just find a regular Sturm Liouville, you just construct a regular Sturm Liouville boundary value problem, solve it, and you will be done. Is it okay? Yes. So here in this theorem, this actually guarantees that you are going to get something like that. Okay. So let's look at the proof. So let's say that let lambda k and lambda l k not equals to l be eigenvalues and phi kx and phi lx are the corresponding eigenfunctions. Okay, of course of star, so that is given of star. Clear? Now since phi k and phi l are solutions, we have this equation, right? Phi 2 of that implies phi 2 of phi k, sorry, plus lambda k r of x phi k of x equals to 0, and p2 of phi l plus lambda l r of x phi l of x, this is going to be 0. Is it okay? Now what we are going to do is, now again same Lagrange identity or Green's identity, which you want to call it. Now using Lagrange identity, I will just call it Lagrange identity. If you want, you can call it Green's identity, no issues there. So using Lagrange identity, you remember, you multiply this thing with phi l, you multiply that thing with phi k, the first with phi k, phi l, and the second with phi k, and then you integrate it, you are going to get this Lagrange identity. So what you are going to get is lambda l minus lambda k integral alpha to beta r of x phi l of x phi k of x dx. Okay, this is nothing but alpha to beta. Clear? Phi l of p2 phi k, yes, minus phi k p2 of phi l. Clear? Dx. Yes. Now, and what is it? See, this is again alpha to beta. You remember that Wronskian part is there, right? So this is nothing but phi l x, sorry, px is there, okay, let me write it here. P2 of phi k, maybe it's okay, let me write it this way. So you see, this is by Green's, right? Direct calculation of Green's. Now if you write it properly, it will be p times the Wronskian. You know, we also talked about it here, p times the Wronskian. So basically this. So then what do you have? Therefore lambda l minus lambda k integral alpha to beta rx phi kx phi lx dx. Yeah, this is nothing but p of x phi l of x phi k prime of x minus phi k prime of x phi k of x, sorry, phi l prime of x, phi l prime of x phi k of x, px times Wronskian of phi l phi k. See, similar sort of thing we got it here also. So exactly the same thing which I wrote here. Now this evaluated at the point alpha beta. So I have to integrate this part, right? See, integration of alpha to beta, this inside this is the Wronskian part, p times Wronskian. So I have to integrate it between alpha and beta. Okay, so now you see, we have to evaluate what happens to this. Yes, now let's understand this. See, since phi k and phi l satisfy the boundary data, right? Phi l satisfies the boundary data. Okay, so what does that mean? It means that a0 times phi k at the point alpha plus a1 times phi k prime at the point alpha is equals to 0. And similarly, a0 times phi l at the point alpha plus a1 times phi l prime at the point alpha, this is 0. And similarly, d0 times phi k at the point beta plus d1 times phi k prime at the point beta is 0. And here also similar sort of thing. Okay, d1 times phi I think l prime at the point beta is 0. So those two conditions are satisfied. Now you see, from these two conditions we have that phi k alpha phi k prime of alpha minus phi k prime of alpha phi l of alpha, this is equals to phi k of beta phi l prime of beta minus phi k prime of beta phi l of beta, this is 0, right? This is what we are going to get. Why we are going to get this? Can you understand what is happening here? See, the boundary data is satisfied, right? Now think about it this way. For this problem to work, okay, see, the thing is a0, a1, d0, d1, this is like an arbitrary thing. It is non-zero also. So basically what happens is this, these two system of equation will have solutions other than the trivial solution. Okay, so the Wronskian has to be the corresponding coefficient matrix, that has to be singular. So basically the determinant can be 0, so should be 0. So basically that is what I wrote it here. Okay, now once this is there, so therefore if you put this condition here, see what is happening is this. Basically it means that this integral between beta to alpha, if you calculate it from here and here, we are going to get this part is 0 because p is given to be positive, and therefore what we have is that will imply lambda l minus lambda k integral alpha to beta r of x phi k of x phi l of x dx. This has to be equals to 0, k not equals to l. Is it okay? Fine. I hope this the logic behind this is fine. See, if you remember again, what is the condition here for this thing to work? a0 square plus a1 square is non-zero, and the condition here is d0 square plus d1 square is not 0. What does that mean? It means that this system has a non-trivial solution. Trivial solution is of course there, but a non-trivial solution. This system has a non-trivial solution. That's what this means. So either one of the a0, a1 or d0, d1, and d0, d1 is non-zero. So if that has to be the case, the corresponding, the coefficient matrix has to be singular. So we are getting this. Now this is basically nothing but this particular thing, evaluated at beta minus evaluated at alpha, which is basically 0. So that will give us this. Is it okay? Now what does this gives you? See, lambda n and lambda k are not same. This is what we assume. Lambda k and lambda l are basically not same. They are distinct eigenvalues, right? So that will imply alpha to beta r of x phi k of x phi l of x dx. This is going to be 0. Is it okay? This is going to be 0 for k not equals to m. Okay, so what does it mean? It means that the set phi n equals to 1 to this set, this is orthogonal with respect to the weight function w of x. Is it okay? So this is proved. Yeah. So what did we prove? First of all, how do you produce an orthogonal set of functions? You just look at the eigenvalues and corresponding eigenfunctions. The corresponding eigenfunctions of our regular Sturm-Liouville boundary value problems are going to be orthogonal. And also, what did we prove? We also showed that the eigenvalues corresponding to a regular Sturm-Liouville boundary value problems are simple. Is it okay? Now in the next this thing video, we are going to look at what happens if they are, I mean, why not complex. Okay, so basically what we are going to show is, we are going to show that the eigenvalues of a regular Sturm Liouville boundary value problems are always going to be real. Okay, that is for the next video. So thank you so much.